In this video, we are diving into a key concept in reinforcement learning, the Bellman equation. It forms the foundation for many RL algorithms. I'll first explain what it is and then walk you through a simple example to help you understand how it works. This is an important step before we move on to actual algorithms. What you will learn here will directly apply to everything we explore next. Before we begin, I want to reference the book Reinforcement Learning by Richard S. Sutton and Andrew G. Barto. If you want to explore these ideas and other ideas that we study in this course, it's an excellent and widely used resource. Now, let's get started. We have seen so far that RL is powerful and can solve complex tasks. We also learned the core ideas of RL: state, action, reward, policy, and environment. We now understand how to model problem with MDPs. The next step is to answer a fundamental question. How do we measure the long-term value of a state or an action? This naturally leads into Bellman equation. We need to answer the question, how good is a state or an action in the long run? And the Bellman equation gives us a set of recursive equations that we can solve exactly or approximately to evaluate a policy or to find a new one. Bellman equation expresses the value of a state in terms of future rewards. For a fixed policy pi, the state value function v pi s satisfies this equation. This is the Bellman expectation equation. For a fixed policy pi, the state value function v pi of s satisfies this equation, where v pi of s is the expected return starting in state s and following the policy pi, pi a given s, probability of taking action A in state s under policy pi, p S prime given state and action A, transition probability from state S to state S prime under action A, and R S A S prime, expected one-step reward for the transition from state S to S prime by taking action A. And gamma is the discount factor, which is between 0 and 1. This is the Bellman expectation equation. It expresses v pi of s in terms of value of successor states under the same policy. But if we want to estimate the best expected return starting from state s, we use the optimal value function v star of s, which satisfies the Bellman optimality equation given as. Here v star s or v asterisk s is the maximum expected return achievable from state s if we act optimally. And max of A, we choose the action that yields the highest expected return. The intuition here is simple. The value of a state is the best you can do from that state. Choose the action that gives you the highest combination of reward now and expected rewards later. Now that we know the optimal value function looks for the best possible future return, two important questions naturally come up. What do we actually mean by expected future rewards, and how do we find the action that gives the maximum total return? To understand this, let's look at a simple example. Imagine you are in a video game. You are standing in a room and your goal is to score maximum points. Now the question is, how many points is it possible to score from this room? Or how good is this room overall? That's the value of this state, V of S. So you have some actions you can take and some rooms you can go into. Each action has certain points. Each room has certain points as well. A room is good if starting from here and playing optimally, you can earn a lot of points in the future. Instead of trying to think through the entire game at once, the Bellman idea is to know how good this room is, just look one step ahead. From this room, you have several actions. Open door A, open door B, fight the monster. Each action gives you some points now and takes you to the next room, a new state, which has its own value. For now, let's imagine a simple game. Each action always leads to exactly one next room, so meaning no randomness, and we'll ignore the discounting for simplicity. We'll add it back in a moment. Step 1 would be to score each action. Suppose from this room, you open door A. You get 5 points immediately. You end up in room X. The value of room X, V of X, is 30. So the score for this action is we will represent it by Q. Q, current room, and you took the action of going into door A. The value is 5 plus 30. So the value for this action from the current room is 35. If you have chosen to open door B, you would get 3 points for that action. You go into the room Y, which has a value V of Y equal to 40. So the action score for this action would be 3 plus 40, which will be 43. And if you instead take the third action, which is fight the monster, you get 10 points now. You go to room Z, which has a value of 20. So the action score for this action becomes 10 plus 20, 30. These are action values. How good is this action from the room? Room's value equal to best action's value. If you are playing optimally, you will choose the action with the highest score. So the value of the current room is the max over all action scores. Value of current room is equal to max of 35, 43, and 30, which is equal to 43. In other words, the value of this room is the best you can do. The maximum over all actions of points you get now plus value of the room you reach next. This is the Bellman optimality idea in the simplest deterministic no discount game. In real RL, we often discount the future with a factor gamma, which is between 0 and 1, called the discount factor. That means the future points count a little less than immediate points. With discounting, each action score becomes points now plus gamma into value of the next room. So if gamma equals to 0.9, the earlier example becomes just 30 changes to 0.9 into 30 for the door A action. For door B, it changes into 0.9 into 40. And for fighting, it changes to 0.9 into 20. And the value of the doors reduces a little. So for door A, it would be 32. Door B, it would be 39. And for fighting, it would be 28. But again, value of current room is the maximum of the best action we can take. So it's still the best action remains going to the door B. If we bring back randomness, an action might lead to different rooms with different probabilities, and use the expected points idea. The full Bellman optimality equation is, in the game analogy, probability P S prime given S A, probability that an action A from this room lands you in room S prime, reward S A S prime, expected points you get from that transition, and V of S prime, value of the next room if you keep playing optimally. The story remains the same. Value of this room is equal to best action you can take, which is equal to expected points now plus discounted expected value of rooms you might end up in next. Now that you understand the Bellman equations, we are ready to explore algorithms that use them to actually solve problems. Next, we'll look at exact solution methods in reinforcement learning. See you in the next video.
To find the entire detailed lesson with all the instructions, math, and code, visit our website edreate.com. There you can find everything you see here and much more. Plus, you can find the full code on github.com/edreate. So don't wait around and sign up now at edreate.com.